Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 14th, 2025, just 3 days ago. This paper shows that the physical laws governing ideal fluids are Turing-universal, meaning fluid motion can theoretically perform any computation a universal computer can. The paper is titled Universality in Computable Dynamical Systems, Old and New, 2507.10725v1, and the implications are pretty mind-bending. It's a survey exploring how these abstract computational models can be embedded within the continuous dynamics of physical systems. Alright, so to understand how this is possible, we first need to look at the fundamental model of computation they use. This figure shows a classic representation of a Turing machine. A Turing machine? Well, it's an abstract model of a computer. It has a tape, which is like its memory, and a head that can read, write, and move along that tape according to a set of rules. The incredible thing is that this simple setup can, in theory, perform any computation. The authors use this as their starting point to show how its logic can be physically realized. So to translate that abstract, step-by-step process into a physical system, the authors represent the Turing machine's tape geometrically. This figure shows what they call Cantor blocks. The blue block represents all possible finite binary sequences starting with a 0, and the yellow block represents those starting with a 1. The next crucial step is showing that the Turing machine's rules can be performed by physically transforming these blocks. These transformations, called block diffeomorphisms, can then be generated by an Euler flow, which is the motion of a perfect, frictionless fluid. Now, the authors explore an alternative to the step-by-step Turing machine. This figure illustrates a concept called a dynamical boardism. A dynamical boardism is essentially a geometric pathway that connects an input space to an output space. Inside, a vector field, which you can think of as a current, directs the flow. As a point travels from input to output, the path it takes performs a computation. This introduces new ways to measure computational difficulty, like topological complexity, which is basically how intricate the shape of this pathway is, for instance, by counting its holes. Building on that idea, this figure shows exactly how such a dynamical boardism can be constructed. On the left, we have a simple finite state machine, which is a basic model of computation with distinct states and rules for moving between them. The authors then perform an operation they call thickening. They essentially inflate this abstract diagram into a physical shape, the dynamical boardism on the right. The original states become entry and exit points, and the transitions become channels for a flow, turning the logical steps into a continuous physical path. So, what's the big takeaway from all this? Well, the research draws a fascinating connection between the abstract world of computation and the physical world of dynamics. The most profound insight is that a universal computer, a machine capable of any computation, can actually be realized within the flow of a perfect fluid. And by using these geometric pathways we discussed, we can begin to measure computational complexity not just in steps or memory, but in the very shape and structure of the physical system itself. That's all we have for this week's AI Research Roundup. Thanks for listening.